Okay, hello everyone. So welcome to this today's session. So today we will continue with our last topic which we have discussed in the last tutorial. So that is bringing the matrix in the upper triangular form by multiplying with the elimination matrix. So now we will see that, so rather than multiplying the two elimination matrix on left side and right side, we can do it together with the combination like an augmented matrix, and then we'll move on to the law of matrices, and then we will talk about the Gauss-Jordan elimination process, inverse process. So let us switch back to our screen here. All of you can see the screen. Okay, so we'll continue our discussion. So in the last tutorial we had taken an example, that is where A is equal to that is 2 4 minus 2 and 4 9 minus 3 minus 2 minus 3 then 7, and B on the right side was then 2 8 10. Now usually we know the general form of writing this is that AX is equal to B. So now it means we have a matrix of 3 cross 3, that is the coefficients of the linear equations that is present in the matrix A, and X is a vector which we have the unknowns, that is a 3 unknowns. So it means we have a vector, one column with 3 rows, and at the right hand side is B, which is supposed to be AX, A into X should be equal to B. So what we have done is this, we brought in the one elimination process here, one common algorithm, so that we can find the values of these unknowns. So what we did to bring that in the upper triangular form was that we have multiplied A and B. We need to multiply A and B, the elimination matrix, separately. Now in this augmented matrix, what we'll do is that we will combine this as one single matrix. We'll combine this row, that is A and B. So we'll get not row, we'll get one more extra column here. So if you see this, now we have this as 2 4 minus 2, then I'll write this later. So 4 9 minus 3, then minus 2 minus 3 and 7, and the one more extra column that is of B is, that is we can write here as 10. So this is what we will get. Now we can straight away multiply this the augmented matrix straight away with the single multiplication process of elimination matrix, and we'll see the result. So let us take this. I'll slightly move this to the right side. Yes. Right. So now let us write our elimination matrix. So basically we are just talking about the one level of elimination. Now when we want to bring it in the upper triangular form, we have to first remove this this 4 from here. So what we need to do is we need to multiply here with some multipliers, so that the first pivot should be equal to this. So the multiplier value is 2. So the identity matrix we have to substitute in that place. So the identity matrix remains to be same as a 3 cross 3 matrix, which is modified to be an elimination matrix by adding 2 at this second row, first column. So 0 0 1. Now let us do this multiplication and see what we get here. I'll shift this entire thing a little up. Let it be here. Now what do we get here is, now here we'll get 2, now here we'll get 4. The first row will be as it is, so 2 and 2. Now if you look into the second row, so what happens is that, just a minute, hold on, I'm getting a call. So let us keep on multiplying these terms here. So what do we get in the next row? That so I'll get 2 4 Can you quickly tell me what the answer that you get here? So probably here you will get this as 0, then you will get here 1, then you will get here 1, 4, then -2, -3, 7, and 10, right? So this was the first step in the previous discussion that we had when we were talking about the previous example. So likewise, we have to multiply with one more elimination matrix to remove this -2. Then we need to multiply, then again one more elimination matrix to remove this -3 by multiplying this row 2. So then we brought in a upper triangular form, and likewise this b also gets changed. So that is what the intention of discussing this topic. So I hope you understood this augmented matrix process. So later we can separate these terms again. So it means I can whatever this triangular form after the final step. This is not the final step because still you have to go 2 more steps here, because you have to remove this and you have to remove this. So once that is done, so now at that time it will be in an upper triangular form. So once it is in that form, so then it's then we can go for a back substitution method and find the values of x, y, and z, the unknowns. Okay, so that was it. So now let us talk about the rules of the matrix. So let me save this page here. Rules for matrix operations. This probably you might all know it. We'll just quickly pass through this. So for addition, the it should be of similar kind of a matrix. For example, if it is a rectangular matrix, say we have 3 rows and 2 columns, so addition should be performed with the same type of matrix. Now if you have 0, 0 here, now a plus, and we have one more 3 cross 2 matrix, then we can perform the addition. So 9, 9. So this is a simple example here. Then we will get the answer as 3, 4, 7, 8, and 9, and 9. And then we can, if you want to multiply with some scalar value with any dimension of the matrix, you can do that. So then it might be 1, 2, 3, 4, then 0, 0. You can do that and you can obtain the answer. So only in terms of multiplication we have to be a little conscious, because in terms of multiplication that we know the rule that the first matrix should be m cross n, then the second matrix should be of reverse order, that is n into p. So then our final resulting matrix will be our m cross p matrix. So this is what the multiplication is. I will not discuss much on that. So I'll straight away come to the laws of this matrix operations. Okay, so now in terms of, we talk about the addition here. So let's talk about the addition law. Then it is nothing but a plus b is equal to b plus a. It means if you can add it in the other way also, it is fine. So this is nothing but it satisfies the commutative law. It is commutative law. Then second is that if we multiply some matrix to an added matrix, a plus b is nothing but, or a c is a scalar value, so if you multiply that, then c into a plus c into b it is same. So this is satisfies the distributive law. Then A plus B plus C is equal to, that is that first if you add A and then B matrix and then add with C, it is same. So this satisfies the associative law. So this is about the addition. Now let us look into the multiplication. There are slight changes in terms of the multiplication of the matrices. It will not satisfy all of these properties and the laws. Multiplication. So A into B is not equals to B into A. So this means that it will not satisfy the commutative law. So it does not satisfy commutative law. Next is C. When you multiply for example a matrix C with to an added matrix A plus B, so then it is same as that is C into A plus C into B. So it means it satisfies the distributive law from the left. Distributive law from the left. So likewise it can be A plus B, then you multiply with C is the same as A into C plus B into C. So this is again the distributive law from the right side. Okay, same as above but from the right side. So then that is A into B into C is equal to AB. It is the order which will matter, means A into B into C. So it satisfies the associative law. So only law that will not satisfy is the commutative law in case of matrix multiplications. So that's about this. Now I'll talk on the inverse of the matrix. Okay, so we'll see how to find the inverse of the matrix. So let me save this page here. So I'll just tell you a simple matrix. For example, we have a matrix A, a 2 cross 2 matrix. So for example, we have a 2 cross 2 matrix. If you want to find, so the coefficients of this matrix is A, B, C and D. So what is its inverse? We know that one of the property of the inverse matrix is that A into A inverse is equal to identity matrix, right? So it will give us an identity matrix. If there is invertible, then it will result in identity matrix. And now let us say this. So it is basically the A inverse is nothing but it is the determinants multiplied by an adjoint of A. So it is, if you want to write in statements, it is the determinant into an adjoint of A. So this is what it means. So how to get this is that now if the determinants is nothing but you cross multiply this, that is A into D minus B into C, then you multiply that with, so only now the inverse method is that we have to reverse this diagonal coefficient. So this will become D and this will become A, and the change the sign of this opposite diagonal, so that is B and C will become minus. So this is the inverse of a method. So here definition is that the matrix A is invertible if there exists a matrix A inverse such that A inverse into A is equal to identity matrix, or this can also be in the other form, that is A inverse into A will also be an identity matrix. Now there are a few things that we have to remember here, so that we'll take it as a notes now. So let me write that note point here. So the first point is that so one more thing is we have to remember not all the matrices has the inverse. Sometimes it might be 0, so that we'll see in the point. So first point is that the inverse exists if and only if elimination produces n pivots. If elimination produces n pivots, it means the elimination solves Ax equal to B without explicitly using the matrix A inverse. Then second note is that the matrix A cannot have two different inverses. This is a very important point. We cannot have two different inverses. So this is the one point. And the third point is that if A is invertible, if A is invertible, the one and only solution, to Ax equal to B is that X is equal to A inverse. I'll write inverse like this. So A inverse B. So this is the way. So for example, if you are doing that A into X equal to B, then we have the A inverse. So if you multiply both right hand side and left hand side by A inverse, then A inverse into A is the identity matrix. So we have only X on the left side. So X is equal to A inverse into B we'll get on the right side. So next, the fourth point is that suppose there is a non-zero vector x such that Ax equal to 0, then A cannot have an inverse. So it means if the right hand side is equal to 0, then A cannot have its inverse. So that is what it means. So if you just look at that, so we can write like this, that is A into X equal to 0, then can only have 0 solutions. Therefore if we take the A inverse, then what will happen? Then when we multiply A inverse on both sides, we'll get X into A inverse into 0, so we'll get 0. It means all the unknown values will be 0. So that is what it means. So the fifth point is a 2 by 2 matrix is invertible if and only if that AD minus BC AD minus it's not magnitude, so that is nothing but the determinants. Okay, AD minus BC is not 0. It means the determinant value cannot be 0. So that is what it means. So then the sixth point is that a diagonal matrix has an inverse provided no diagonal entries are 0. No diagonal entries are 0. So this is another method. So this is about the important points that we have to remember when we are doing it. Let me save this page here. Okay. So now let us see a few important things here, that the inverse of the product of two matrices. For example, if it is A into B, then what is its inverse? So A into B is equal to, we can find individual inverse. So B inverse into A inverse also results in same thing. Yeah. Then A into B multiplied by B inverse into A inverse. What do we get here is that, so we will get here as A identity matrix of A inverse, so that is nothing but ultimately we'll get there an identity matrix. That's it. So yeah, so now let us talk about the elimination matrix. Now what is the inverse of an elimination matrix? So in the previous tutorial that we have seen, we have used one elimination matrix, that is E. That is E is nothing but there was 1 0 0 minus 5 1 0 1 0, sorry, 0 0 0 1. So this was our elimination matrix for the previous tutorial example. And how do we find the inverse of this E? So E inverse is simple. So there what we had done to obtain this elimination matrix is that for an identity matrix, so for example if I take an identity matrix here, so identity matrix was 1 0 0, then it is 0 1 0 0 0 1. Now for this identity matrix, to obtain this elimination matrix, I multiplied this row 1 with 5 and subtracted with equation 2. So there, so that is how I got my minus 5 here. So now it is a reverse process. So now rather than subtracting, so I'll get 5 here. So this identity matrix will change to the elimination matrix. Now rather than subtracting, so for the same identity matrix, what we need to do is that we have to add it. So we have an identity matrix. So 1 0 0. So now this is 0 1 0. Then this is 0 0 1. So now what we'll do is that to obtain the inverse of E elimination matrix, so now we will multiply that same multiplier, that is 5, to row 1 and add with row 2. So what do we get now is that we will get here the value as plus 5. So now this is nothing but our inverse of E, that is the elimination matrix inverse. So likewise we had one more elimination matrix, that is F. So F was that 1 0 0, then 0 1 0, then 0 minus 4 1. So what we did was that we have multiplied 4 to row 2 and then subtracted from the row 3, then we got this minus 4 here. So what is the inverse of this F? So inverse of the F is the same thing. Now instead of subtracting, we will add in the identity matrix, so that we will get this as 0 0 0 4 1. So now this is our this thing, inverse of F. Now let us see here some interesting thing. So I'll just remove this part which is not required, and I'll move this entire thing above. Okay. So now what about E into F? So if we try to find that E into F, what do we get? So E is this matrix. So I'll just write, I'll just shift this and I'll bring in my, so this is my E inverse, let it be there. Now F is nothing but, it is 1 0 0 0, this is 1 0 0 minus 4 1. So when you do this, what is the matrix that we'll get? We'll get here 1 0 0. Then here we'll get this as 1. Here we'll get it as minus 5. Then here I'll get this as 1 0. So now here, if you see that, we'll get here sorry, it was my mistake. So we are supposed to do F into E. We're supposed to do F into E. So let me interchange even these terms. I'll move this term here and then move this term here. You keep it. Now you move this here. Yeah. So now it is F into E. Let us multiply this. What do we have here is 1 0 0. So now let us multiply this second row. What do I get here is that minus 5. So then I'll get here 1 and here I'll get this as 0. So then this last row you multiply, you will get here 5 4s are 20. Then here you will get here as minus 4. And then here you will get this as 1. Right? So this is F into E. Now if you try to do now I'll remove this part here. So if you try to do the inverse of this E inverse with F inverse, then what do we get? So let me take this E inverse part here and let's see what we get. So if you try to find the inverse, E inverse into F inverse, do we get the same thing? Now what we get here is that not same thing, it is the inverse we are trying to find. So F into E will get this, then inverse, what do we get? Let's see. So it's just multiply, so I'll get here 1, so then we'll get all here as 0 0. So now we multiply this, we'll get 5, then you will get this 1 0. So now you'll get here the term as the last term, so this will get as 0. So next term we'll get this as 0 and this will get it as 1. So here the last term we'll get it as, sorry, this is 4. So I'll get here as 4. So if you say this, so F into E is this term, and then if you look into the inverse, we'll get this term. So here the missing term is that this 20. So now this is nothing but, so here in the E and F we have one extra term, that is here 5, and in F we have this 4 that we have added. So that basically is nothing but 4 into 5, because we have multiplied the first row with 5 and added with row 2, and here we have 4 that we added. So basically it means that that 20 will fall, that 5 into 4 we have to multiply, and fall below the diagonal matrix. So this is one of the example of this, and then we will discuss on Gauss-Jordan elimination process. What's the time we have? We have quite a time. Okay, let us discuss on the Gauss-Jordan elimination process. This is very important because we will not going to follow this method to find the inverse anymore, because when the order gets increased of this matrix, then it is difficult to follow this method, these determinants and adjoints. So I'll go for this Gauss-Jordan method for the elimination to find the inverse of these elimination matrices. So let me save this page here.